So hello, I'm Giulio Alessandrini. I'm the lead developer of machine learning team. I used to give talks about image processing mostly before because I was in that team before coming here. So I'm still a bit biased regarding applications. But today I'm gonna mainly try to give an initial overview about where we started with automated machine learning in the Wolfram language, and what we are doing now, and where do we go from there. I also put a couple of polls in the page where basically one is just basically to know where you're coming from as users, and the other one is I will mention some directions that we would like to explore. So at the end, feel free to star vote, demand some more effort in a specific direction. I always appreciate the feedback. Okay, let's start. So I went back to the documentation, and because I wanted to have a look at how our machine learning story developed over the years, and something I never knew, but some others are interesting. Like I think this one was version 10.0. So it was the first version where we had actually any machine learning kind of officially marketed as that capability in the Wolfram language. And we started with the two functions that have been carrying the framework over since the beginning. So they're classify and predict. I'm going to talk about them later. So, and I think most of you know what they do and what they are. Then it was a time shortly after, with like even before the neural network framework, we had image identify, and that was a huge project. I'm also on the web, but was kind of a moving the first baby steps in deep learning. And soon after, text cases, which I hope you have played with, a very nice function has been recently extended, very powerful, to do auto tagging of text. And then there was in 2017, okay, and 2016, the big addition was quite a revolution in the team with the net train, the net graph, net chain. So like this is when we started adding deep learning capabilities, and plus in the meantime the classical ML part, if you're not familiar with that, was also growing. We have dimensionality reduction functionality since almost the beginning, feature extraction functionality, stuff that I'm gonna like briefly talk about today again, and then we had downloadable models, which is something that we are still very much committed to. So I think Shadi mentioned that yesterday. The neural net repository is hosting a handful of new video models to accompany the new influx of video functionality, and we are going to add more in object detection to mirror our effort in machine learning here that I'm going to talk about today, and more. I think they are always coming. And we are trying to keep it in sync with the rest of the language. We added audio support in 2017. We have been adding video support this year, and to make life easier. And for this, we had a whole sort of surgery function that I think makes very nice to play with networks as symbolic objects, and nice monitoring and automation capabilities. And I'm going to elaborate a bit on this later for the core machine learning functionality. Plus add a bunch of side functions that you might or might not know, like learn distribution that can learn distribution of arbitrary data and can be used to synthesize missing values, and can be used to find anomalies in the data sets, and a bunch of functions here and there. So like this is a story that we've been telling up to this point. And I want to briefly go through the capabilities of the framework right now, and then spend the last part discussing present and future. Okay, so I realized that we never really show much about like we are very focused on one-liners. We've never shown much how to deal with the whole machine learning pipeline. There are a bunch of standard steps that people usually take when they have to analyze data with machine learning. And I put like kind of a broad categories here, like you want to get your data in, you want to clean it, you want to decide what part of the data you want to look at, then train some model, and then use it to perform some analysis. So given that some of these things are often overlooked, I want to start with the beginning. And so this week I went on Kaggle, and I found a classification data set that I never used before. This was heart disease database. And it's actually a series of databases. I put the link in the notebook. I believe this is available if you want to download and play with it while I talk. And actually the link in Kaggle is this one. But I also put the original link for a reason that will become apparent right now. So, okay, I have this stuff in my WTC folder. From Kaggle, you can download a zip file. So you can extract the content of the zip directly from the Wolfram language with extract archive. And then you can have a look what's in here. So this is a data set that aims to predict if there's likelihood of a heart condition given some other features like electrocardiogram, like ECG lines and age, sex. I mean, usual measurements. And having a look at these files, you immediately can see that you can do better. So we have very nice CSV import. So I can say like import this as a data set with one header line, and then you immediately have the data. Like in this format, I can already train, for example. There's nothing more I have to do. But for the sake of the argument, let's go through a few more things. So let me save what are the keys in this data set. And let's see why I put the original data set in. Because actually the original data set is not very clean, but has a lot more data. And we have the capability to do better with that. So here I'm importing, these are data from 4 different research institutions. I'm just importing all of them, putting them together, and this is what you get here. So you see there's a bunch of question marks that they are basically missing measurements. Some data sets, they come with different formats. So this is a kind of a more real world dirty, like not super dirty. It is a rectangular array at least, but a little dirtier than our usual prepare research data. But it's actually very easy to analyze this stuff because, for example, I can use map@, to round up all the wrong columns that are not they're supposed to be integer but are not. I can use a quick call to replace all to convert all this. I'm just being lazy here and applying round to everything and then changing round question mark to missing. And then I have something like this, and this is a lot more palatable in the language. Again, I could train directly with this, but let me add back with a couple of transposition, the keys to go back to the original format that I had before in that CSV file. The difference is that now that we went to the original source, instead of having, what was it called, this Kaggle? So instead of having just 303 data points, we have a lot more. And we have 920. So, okay, now that I have the data in, what can we do with that? First thing is I can take a look at that. And given that not all data sets, all the 4 data sets have, like if I look at these, I can see that my heart condition is sometimes 0, 1, 2, 3. Some institutions, they collect actually, this is okay, this stuff is not okay. But some others just have like 1 and 0. So it's not good to have like these different formats. So here I'm just using sign to convert the 0 to 0 and whatever to 1. And I have just 2 classes here. Then I'm getting features and targets. by separating like what I want to predict from the normal features, and this is a typical way I can use to start having a look at what this looks like. So we have this dimension reduce function that takes both like very classical methods, neural network based, more advanced newer methods, and this was like recently added for 13. And once I've done that, I can create like some nice plots to see that yeah, the just linear separation is not probably be enough to have good predictions. It's not sometimes you have clear clusterable data points. In this case is not so obvious, but like more advanced methods can still do a almost decent job at doing like almost pure clusters. So there's maybe some hope to get information out of this. And let's go ahead. So okay, classical thing that we have not been focusing much up to this point, but I would like to get a bit of improvement in this department is feature selections. So the way it works now, it's mostly based on feature extraction. And you can see like if I can train on my dataset a feature extractor, and in this case, I'm asking for a function that I can apply to new data and some extracted features. And let's look at these features, how they are. So from all those like list of nominal real variables, now I get just a vector of 30 elements that is basically ready for most classification methods. And I can see basically what was inferred automatically. Like this is what the framework is taking on. Like you can specify how you want each variable treated, but this is like a first step of the automation. Like automatically figure out that age is a numerical value while sex is a Boolean value. It could only find 0 and 1. Some other are nominal values, and these are the three types that we have in this data set. And we have been pretty open with the structure of our functions. So there's a very powerful processing capabilities inside here, and you can actually look at that. We try to make it, I mean, this is internal stuff, so we don't guarantee it will never change, but it's curated in a way that I think it's nice to expose to get a bit more information about what's going on. So you see like this part of automation, like figure out how to do, like what to do with Boolean vector, nominal vectors, numerical vectors. They are going to different pipelines, they are conformed. Nominal vector are embedded in a continuous space, and then at the end you just have one big numerical vector standardized. So this is like in this case, the feature selection is mostly done by the dimensionality reduction here, and but you could do this on your own, and this is one sector where I would like to add a bit more functionality in the coming versions of the language. So right now, the feature extraction is going to be the base for taking out vector data from whatever form of data you have. Okay, so now that we have the data in a numerical form, it's like training is actually very easy. So I'm going to do the usual split test train. I'm taking 300 for testing later. The rest is for training, around like 700 something. And then I use this nice syntax of classify. Say this was a whole data set structure. Let's look at it again. This is done this way. This contains all the data, all the categories, including at the end what I want to classify. It's like 0, 1 condition. So what I do is just say classify. You have a data set, say classify the target column. We automatically drop all the target column from the input data and use it as an output. And I can classify exactly what I want to do. For example, here I'm saying like I wanna try logistic regression, and I can specify all the parameters of my logistic regression. Like for example, this stuff has a nice documentation page that okay, being full screen is never nice. Let's okay. I should probably go out of full screen to do this. So you see this method here is method of classify, and you get all the options, you get examples. So it's very easy to understand what's going on in this case. And where's my other notebook? I guess it went somewhere here. Okay. So let's do the training. This is going to be very fast, so we can do this real time. I get a classifier function. I can look at that. So we see exactly what happened. It tried on the different subset of a data set, starting from like just a few examples till the full data set. This already tells me some useful information, like how accurate it was on the training set, how fast it is on a single example, on a batch, how heavy the model is, how many examples have been used, like 620. And in this case, I get just estimation of the accuracy. So this is this 81 that I see here. This is a very interesting thing, but we are going to discuss this later because it relates to the automation. And right now, there's not much going on here. Of course, this now is a normal mathematical function that they can apply. And I will just take test. This is still the full data set, but it's not using the target column. It knows that to drop it and actually give me a prediction here. Okay. Now that we have the classifier, how we can analyze this? So we have been introducing since like many versions ago, classifier measurement function. This I can provide new data, in this case a test set, and it's going to tell me some more information about what's going on in terms of measurements. So here it measures the accuracy on the test set and gives me like a little bit of information. This is very useful confusion matrix plot. Like this diagonal is a perfect classification. These 30-30 were the misclassified examples. And there's actually a lot of properties. Like you can query for a specific function, like some standard measures. We have F1 scores. We have precision, perplexity that you can query, and you can also plot like a bunch of visual representations of these quantities. So like this is the receiver operator characteristic curve, and like tells me like to get everything correct, how much do I have to lower my expectation and bring in false positives. So like here would be perfect. We have like this was a pretty noisy data set, so there's still some problems getting super high. But yeah, this is very useful to understand basically what's going on. You can check that the probability estimation that you get from the classifier is properly calibrated in terms of actually real probability of the result. And there are new things that you're working on, like for example, this thing here. I hope it will make it to 13. This is sharp plots, like Shapley values, and it's going to tell you like each features, what impact it has on the probability for each class, on the log odds actually for each class. There's most of this in the talk by Jesse, which is coming after mine. It's all about explainability. So please go to that. It's very interesting. And it's one of our focus areas, but more on that later. And so that said, there's a lot of stuff that I don't really need to do to start training. So okay, now the thing that was here that I didn't mention, like here I put the original data, but I say the extract the features with the feature extractor that I trained before. And this feature extractor can also be specified, like decide what to do on every single feature. The nice thing is that you can do this, but you can also go directly to classify and ask classify, like just get this data with all the missing content, like raw data can be, Boolean, dates, quantities, and just do a classification. So in this case, what it will do, it will try a lot more things. If we look inside now, we see that okay, the loss is going down. That's nice. The more data we use, the accuracy is going up. But this stuff was basically this is the core of our automated ML capabilities. So like all the methods that make sense of the data are tried and with different parameters, and And classify internally will manage the time budget that it has in order to basically get the most out of the time. Some methods are faster, some methods are slower. It's not always worth to try everything on every type of data. So in this case, in the end, it ended up on reduced regression, and actually it did a bit better, actually, 4 points more than with a bit of variation though than what we did manually before. And this is always a good entry point. Like if you are not sure about what method you should use, you might still try custom things. You're encouraged to do that, but kind of this is a baseline that you want to beat. And sometimes even if you want to train some deep learning functionality, is still worth it to try some classical approach first to see what's a decent baseline that you want to beat. Okay, so I showed you a bit of internals before. You see, like in this case, we are using logistic regression, so we are gonna end up with final, like actually this we can take it with nominal vectors as well. Like we don't need, one of the advantage of extracting features together with classification is that depending on the method that you choose, you can do different pre-processing, but you can still follow what's going on here. And you can take out the model and see exactly what's going on. In this case, you can extract the layers, the linear coefficients that I used. You can look at all the parameters inside. There's a lot of stuff that you can look at if you're curious about what exactly is going on here. Okay, we don't have so much time, so like this is kind of our state of the art right now of the automation. Where do we want to go from here? So current direction, our first one that I really care about is how Jesse puts it, is human in the loop. So interpretable, explainable machine learning. This is the link to his talk, but it's just after mine. And so we are adding a bunch of useful instruments to basically gauge how a black box model is interpreting the data. And we have like the IC plots, the conditional expectation for each features. And let me show you here. Basically, the idea here is that you can follow, so this is data set to explain wine quality with other features. And you can basically fix all the other features and see how each examples will move in the feature space if you change, for example, just the fixed acidity, volatile acidity. So we can immediately see there's a bunch of bottles that everything else being constant is going down in expected quality, increasing the acidity, or is going up, increasing sugars. Like this is very useful to basically probe the insides of these models. And we also have classical sharp values that they were added last version. We are trying to add more plots to get a decent estimation of what's happening to a whole data set. So this is still the same wine data set. We see, for example, here, like density, high density is affecting negatively quality, while low volatile acidity also is affecting negative quality. This is the Titanic data set is another classification data set. And you can immediately see that two different sex classes have very different, I think this is just the survive, or I mean, this is the mirror of the dead outcome plot. So like we want this and more. Actually, we want really people to be able to look at what they trained and figure out why you get a specific answer. Another huge thing that we are working on right now, we just came out with this, and we want to keep focus on this for a while, is trainable content detector. So as I showed you before, we added functions like text cases, image cases, where you can not just identify or classify the main content of a picture of a piece of text, but you can actually look inside and find out subparts, what they are, and tag them. So this is an example that I can show you real time. I think this was also in Steven's keynote. You can create this new object, content detector function. This will tell you this is for text, and will find fruit and sport classes. The idea is to make it work properly with even minimal inputs. There's a lot of fine tuning, a lot of data augmentation for the image part. So we want simple syntax, that's the goal, and a powerful result. Once you have this function, so these classes are not present in the standard text cases. So we are just going to add them. And now you can apply this text to new text here. And bam, you see, okay, this I ate cranberries is fruit. I like basketball is sport. You can query it, so like this is one function with some properties. You can ask the position, the probability, if you want to do further analysis. This is a very similar syntax for images. We have these kind of big important names. We're still working on something that can be super fast. So we don't want to call this content detector yet. As soon as we are ready. So this is like kind of experimental version for the first round, but it's already pretty powerful. This is a particularly small data set, so I wouldn't expect much from this, but it's already getting out something by virtue of doing a lot of fine-tuning and augmentation of these images. So here I'm adding like this kind of fruits, strawberries, apple, bananas. Here I imported one that I trained just before, like in half an hour or so before this meeting. Which is not a long time if you know how much it takes to train one of these from scratch. And then like let me make this bigger. This is another banana. And now it's telling me this is the image and it's compared to the string above, and this is the class. I can again here query for more properties, get the bounding box out, the position of the center, the probability, and I can display this. Like our usual image functionality on top of the input image. So this is kind of our present direction. Where do we want to go from here? So immediate future is we want, of course, more automation. Like we want to go back to the sequence prediction and unsupervised learning and add a ton more automation there, like hook it up on the same automation mechanism that we use in predict and classify. We want to give more control and more powerful automation on data pre-processing. Right now it's mostly type-based, but there's a lot more that can be done here. And there are a bunch of future directions in terms of application areas that would really like to add to the language. One of those is probabilistic programming or Bayesian data analysis, if you know that. Which basically you can write your distribution, let's say, as like small programs. Is very easy to write, and then you can condition those programs with the observation, and then go inside and see how the parameters have changed. So like this I think was something for logistic regression that I tried with 2 parameters for linear transformations, and how they are beginning with no prior and how they become after you show them some real data. Then there's reinforcement learning that we have been added very limited capabilities, but we want to go back to this. And another direction is going to be graph neural networks, which is very powerful and right now is not present in the language. Okay, so just on time, actually a little late. Thanks for being here. Let me address very quickly some of the questions that have been asked. Yes, UMAP is implemented. You will find it in version 13. Detailed views of variometrics, not really right now, but one of my goals is to dramatically improve the documentation of our machine learning functionality. So all the methods are already pretty well documented, but some other aspects are not. So that's going to come in the future versions. Not yet all for 13, but a lot more is going to come. And Bayesian machine learning, yeah, we want to tackle that a bit on the side with probabilistic programming, but we still need to see what these last few things are not fully prioritized yet, but is, let's say, our wish list for the next few versions, kind of medium term. Thanks for attending, and I'll let you go to the other talks. Please go to Jesse's talks. It's going to be nice. Thanks. Bye.